Welcome back. In this lesson, we will focus on one of the most practical but often underestimated parts of front-end planning: existing conditions, site analysis, and early risk identification. Construction projects are never delivered in an abstract environment. They are built on a specific site, under specific regulatory conditions, with real physical constraints, utility limitations, environmental issues, and sometimes ongoing operations nearby or even inside the project area. That is why existing conditions should not be treated as a simple engineering checklist. They are a front-end planning issue. They can determine whether the selected project concept is actually feasible, affordable, buildable, and practical to operate. The key question during front-end planning is not only what do we want to build? A better question is, what must be true about this site for the project to succeed? If the team does not verify site knowledge early, the scope, cost estimate, and schedule baseline may be built on assumptions rather than facts. Unknown utilities, weak soils, limited access, permitting constraints, hazardous materials, or insufficient utility capacity can all change the project after major decisions have already been made. The central lesson is simple: there is no reliable scope, cost, or schedule baseline without verified site knowledge. The central lesson is simple: there is no reliable scope, cost, or schedule baseline without verified site knowledge. A structured site analysis gives the project team a disciplined way to identify conditions that may affect design, cost, schedule, safety, construction logistics, and long-term operations. During front-end planning, site analysis should not be done simply to produce technical reports. The purpose is to determine which conditions create project risk and which decisions must be made before the project moves into detailed design and construction. There are 5 major categories to consider. The first is physical site constraints. The team needs to understand where the facility, access roads, staging areas, cranes, laydown zones, temporary facilities, and safety controls can realistically fit. These constraints can shape site layout, logistics, phasing, and even the delivery method. The second category is surveys and subsurface conditions. This includes property boundaries, easements, underground utilities, soil conditions, groundwater, rock, seismic considerations, and flood risk. These factors can directly affect foundation design, excavation cost, and schedule contingency. The third category is utility capacity. It is not enough to know that utilities exist near the site. The team must verify whether water, sewer, electrical, gas, data, chilled water, steam, fire protection, or other systems can actually support the proposed facility. The fourth category is environmental conditions: wetlands, hazardous materials, contamination, noise restrictions, air or water discharge issues, and protected species can all affect permitting, remediation cost, sequencing, and stakeholder coordination. The fifth category is permitting and regulatory requirements. Permits are not just paperwork. They can become critical path activities, and in some cases, they may determine whether the project concept is feasible at all. The important point is that these categories are interconnected. A drainage easement may affect building placement. Building placement may affect foundation design. Foundation design may affect excavation duration, and excavation duration may affect the schedule baseline. Site analysis is therefore an integrated planning activity, not a collection of separate studies. Renovation and brownfield projects require an even deeper level of existing condition investigation. In these projects, the team is not simply building on an empty site. It is connecting new work to existing structures, old systems, active operations, and documentation that may be incomplete or inaccurate. One of the biggest risks is that the team may believe it understands the existing facility based on drawings, reports, or owner memory that no longer match actual conditions. In renovation and brownfield work, assumption is risk. Verification must happen early. First, the team must verify as-built information. Older facilities often contain decades of undocumented modifications. Pipe routes, ductwork, electrical panels, wall assemblies, and structural openings may have changed over time. Field verification may require test pits, selective demolition, utility tracing, ground-penetrating radar, or 3D laser scanning. Second, the team must assess existing systems, structural capacity, mechanical systems, electrical systems, plumbing, fire protection, building envelope condition, code compliance, and remaining service life all need to be confirmed before the project assumes that existing systems can be reused. Third, the team must plan for operations. Brownfield and renovation projects often occur while the facility continues to function. A hospital may need to maintain patient care. A university may need to continue classes. An airport may need to process passengers. An industrial facility may need to continue production. That means shutdown windows, utility tie-ins, access restrictions, noise and vibration limits, safety procedures, temporary utilities, and phasing plans must be identified during front-end planning. The planning question becomes, can this be built here while this facility continues to function? That question is essential for renovation and brownfield projects. The value of existing condition investigation becomes very clear when we compare early discovery with late discovery. The same physical condition can be manageable during front-end planning but highly disruptive during construction. For example, if a utility conflict is identified during FEL1 or FEL2, the team may still be able to compare alternate layouts or adjust the site concept. The cost and schedule impact may be relatively low because the project still has flexibility. If the conflict is confirmed during FEL3, before baseline approval, the team can still revise the design, estimate, schedule, and risk register before authorization. The impact may be moderate, but it is still manageable because it can be included in the baseline. If the conflict is discovered during detailed design, after major design decisions have already been frozen, the project may need redesign and drawing revisions. At that point, the cost is higher and delay becomes more likely. But if the same conflict is discovered during construction, the consequences can be severe. Work may stop, the team may need emergency redesign, change orders may follow, claims, delay, and productivity loss may become major issues. This timing effect is one of the most important principles in front-end planning. Early investigation does not make every problem disappear. Instead, it moves discovery into a phase where the team still has options. Starting construction before the site is understood may create the appearance of speed, but in reality, it often transfers hidden risk into the most expensive phase of the project. Front-end planning protects the project by making uncertainty visible before the owner commits major capital. Existing condition analysis should not end with a report. During front-end planning, site findings should be converted into a site-specific risk register. The goal is to make site-related uncertainty visible before scope, cost, and schedule commitments are approved. A strong risk entry should clearly describe three things: the condition that creates uncertainty, the event that could occur if the condition is not resolved, and the consequence for cost, schedule, safety, permitting, or operations. This is called a cause-event-consequence structure. For example, a weak risk statement might say, utilities may be a problem. That is too vague to support decision-making. A stronger front-end planning risk statement would be, if the existing electrical service cannot support the laboratory program, the project may require a utility upgrade that increases cost and delays commissioning. This version identifies the cause, the possible event, and the consequence. It also helps the team decide what to do next. Should the risk be reduced through additional investigation, avoided through a different layout, transferred through contract language, or accepted with appropriate contingency? Typical site-related risk sources include geotechnical uncertainty, underground utilities, insufficient utility capacity, hazardous materials, environmental approvals, permitting duration, restricted access, and shutdown or tie-in requirements. Each significant risk should have an owner, a mitigation action, a due date, a status, and a clear link to the decision gate it affects. The risk register becomes a bridge between existing condition knowledge and the project baseline. If major site risks remain unresolved, the project should not present the same level of cost and schedule confidence as a project where those risks have already been investigated and mitigation actions are underway. The Bertha Tunnel project in Seattle provides a powerful example of late discovery in practice. The project was part of the Alaskan Way Viaduct Replacement Program and involved a large tunnel boring machine operating beneath downtown Seattle. This was a dense urban subsurface environment where underground conditions and prior site activities carried significant risk. A major disruption occurred when the tunnel boring machine struck an existing steel well casing during execution. At that point, the machine was already underground. The issue was no longer a planning problem. It had become an execution crisis. Recovery required extraordinary measures, including construction of a deep access pit to reach and repair the machine. The result was major schedule delay and significant cost overrun. For front-end planning, the lesson is not simply that underground conditions are risky. The deeper lesson is that existing conditions must be investigated, documented, and carried into the project risk register before the execution baseline is approved. A subsurface condition missed during front-end planning does not disappear. It remains embedded in the project as hidden risk. When it appears during construction, the project has fewer options, less flexibility, and a much higher cost of response. This case also shows why subsurface surveys, utility mapping, and historical site records should be treated as critical front-end planning deliverables. These investigations must connect to design decisions, construction means and methods, contingency planning, and schedule risk analysis. The goal is not to know every underground condition with perfect certainty. The goal is to identify the most consequential uncertainties early enough for the project team to act. That is the real value of early existing condition analysis. It turns hidden risk into visible planning information before the project reaches the point where change becomes expensive, disruptive, and difficult to control.